Hello everyone, let's solve this LeetCode problem 997, find the town judge. And it says in a town there are n people labeled from 1 to n. There is a rumor that one of these people is secretly the town judge. If the town judge exists, then the town judge trusts nobody. Everybody except for the town judge trusts the town judge. There is exactly one person that satisfies property 1 and 2. And here the trust is basically uh, an array, and in this array is basically a directed graph. And each element in this trust array, for example, 1 and 2, if this is an array, then it means person 1 trusts person 2. And if you have another example, 1, 3, then person 1 trusts person 3. And similarly, you have another element in this example right there that person 2 trusts same person 3. And here you can see that person 3 does not trust anybody. And given this input, and n equals 3 in this case, n is just 3. So there are three uh, per people, and number 3 doesn't trust anybody, and everybody trusts number 2, so 3 is a judge. But in case if you had this if you have this case that number 3 also trusts number 1, just in this case, in the third example, uh, you'll notice person 3 also trusts person 1. So in the case, there is no one who can satisfy these two conditions. So in that case, the result will be -1. So there are different ways of solving this, but it heavily smells like a graph problem. So one way of solving this graph problem is to go through all these edges. Each trust array is an edge, and if you just go through all the nodes which are not in the first position of the edge, that means uh, all the edges. So in one way of solving this is to go through all the edges. Let's say 1 and 3 and 2 and 3. If you go through each one of them and take the first one, so these nodes trust somebody else, right? So you are also given an edge number of nodes here, and equals 3 in this example. And if there are 3 nodes, right? And each node represents a person, and person 1 trusts person 3. So it cannot be the judge. Person 2 also trusts person 3. It cannot be the judge. You can go through this kind of elimination process, and eventually you will have to scan through all the nodes, which does not, which node actually doesn't trust anybody. It does trust someone, node 1, node 2 trusts someone, but node 3 doesn't trust anyone. So if you had at a marker, you can see that person 3 is probably one of the candidates as a judge. Then you can see that everybody uh, is actually trusting the person 3. So one way to just go through all these nodes first in order of E, where E is the number of edges in the graph, and each edge is between two nodes, and the nodes represent people. And after that, you can go through all these nodes to find out the potential judges, and then again, you can go through the edges again and see if that node is trusted by everybody. That's one of solving it, but there's a better way. So let's say 1 trusts 2, 3, and 2 trusts 3, then you can see that if you had a table with numbers uh, for the node, let's say uh, 1, 2, and 3, you had a table like this, and you know that person 1 trusts person 2, so there is an outgoing edge. So out and in. So outgoing edge means who it trusts. So person 1 trusts uh, person 3, right? So it trusts somebody. So he trusts one person, and person 3 is trusted by person 1, right? Sorry, I need to update my drawing. It's a bit messy. So person 1, person 3, and person 2 also trusts person 3. And if we had an input like this, 2, 3, so this is our input. Okay, person 1 trusts somebody, and who does it trust? Person 3. So person 3 gets trusted by one person. And then person 2 uh, trusts person 3, right? So person 2 trusts somebody, and who does it trust? So you're counting all the incoming edges and outgoing edges. And in this case, you will see at the end that all these nodes are n here is 3 and n minus 2 is 2. And you will see that only node 3 has two incoming edges and there is no outgoing edges, and that makes node 3 the judge, and none of the others actually have n equals to n minus 1 edges incoming. So you can do that. You can also do just one. So in this case, you'd have to have two arrays to track the incoming and outgoing edges. But you can see that what we care about is the difference between the incoming and the outgoing. So you can actually just sum them up in one single array. So if you have a difference table, in this case, you have n equals 3. So there are three, um, three nodes, and for each node, if you go through the list of arrays, let's say 1, 3, so first one, second one. So for 1, 3, the first node is the outgoing. So for outgoing, you just subtract 1. It's currently 0, and you just make it minus 1. And 3 has an incoming edge, right? And then this becomes from 0, we just add it by 1. And every time we have an incoming edge, we just add plus 1 to this counter, and the counter starts with all zeros. And if it is an outgoing, we subtract it with 1. And for the next node, next edge, 2 is the outgoing, so we subtract minus 1, and it becomes 1. And 3 is the incoming, so we just plus 1 another time, so this becomes 2. Right? And the end, if you just scan through all these nodes, you will see only this one has an counter of n minus 1, which is 2. And that makes us the judges. So that can be solved using order of n runtime, because you have to go through all the, it can be order of edges first to go through them, and then finally you have to go through all the nodes together. So the total runtime complexity is order of e plus n. N is the number of nodes and is the number of edges, and the space complexity would be order of n. So now let's solve this problem. This is going to be very simple. But remember that the nodes actually start with 1, not with 0. So in this case, we can create an array. This is going to be a new integer array, and n is already given, and for each integer array edge in trust, we can see in out diff array, we can see the first one in the edge, and we can subtract 1 to get the index, and we can, for this first value in this relationship is outgoing. So for this one, we're going to subtract the value, and for the second node, we are just going to increment the value. So this gives you the counter. And finally, for I equals 0, I less than, for every node, what you can do is if I equals n minus 1. So in this case, we will just return I plus 1 because we add plus 1 because the actual index and the labels of the nodes have start with 1, so we just add 1. But otherwise, in our array, it is just going to be going to start from 0. And if there is no such value like this, what do? We just return minus 1. So let's say if we can satisfy the first three. So we have already seen the second example. And if we had the third example, in this case, the third one will actually make sure that node 3 is trusted by both, but node 3 trusts number 1. So for node 3, the third example, we would have actually this table. So 1, 2, and 3. These are three nodes, and node 1 is first 1, 3. So we add to 3, but we subtract 0 from the first node. And 2 to 3, so we subtract to 0 becomes minus 1, and node 3 becomes 2, which is increase another 1. Then 3, 1, here is a dependency to 1. So node 3 again becomes 1, plus 1 because we subtract 1, and plus 1 gets incremented, so this becomes 0. So the final is 0 minus 1 and 1. This would be the final state of the 3 node array, and this is going to make sure it's failing. So we can submit, and it passed.